Every time a patient is discharged from the hospital, he is assigned a code, an ICD code, or you also call it International Classification of Diseases. Now that determines what the hospital bills, what the insurance company pays, and what ends up being as the patient's data. Now in US alone, there are like 70,000 of such ICD codes, and hospital processes thousands of discharges every day. Now, this is not a general purpose problem. It's not about something you can look up in a textbook. It's a precise high stake mapping task. Take a clinical note written by a physician late in the night, sometimes ambiguous, sometimes abbreviated, and map it to the exact right code. Now, if you get it wrong, there might be an insurance claim failure, and if you get it consistently wrong, then you are looking at a compliance audit. Now ask a general purpose model to answer this question, a model which can do, or a model which knows a little bit about everything. It might give you an answer, it might even sound confident, and for simple codes it might be even right. But if you ask a very specific question like what is the difference between J18.1 and J18.9, or difference between sepsis and severe sepsis, or handle the way a hospitalist would write a note at 2 a.m., and that's where general model fails. A model fine-tuned on clinical text does not struggle with that. It's been trained exactly on that language, it speaks that domain. Now that's the difference between a general purpose model and a domain specific model, and the difference in production, in scale, in system processing thousands of claims every day is what this video is about. So before we build anything, I want to address something directly. So in the last video, we built something called RAG, Retrieval Augmented Generation. We ingested some document, we used an open source model, and we retrieved the relevant chunks and we fed it to the model, and the responses were great and it worked pretty well. So the obvious question is like, why can't we do the same thing with ICD codes? Because the problem here is different. RAG is the right tool and it shines when the knowledge is in the documents, like the PDFs, the articles, the policies, the internal wikis. When the answer literally lies somewhere and you just need to find it and synthesize it, the model's job is to just read it and summarize it. Now, ICD coding is not a reading problem. It's a reasoning and mapping problem. The model needs to have internalized the clinical language, the abbreviations, the diagnostic logic, the patterns. Now you can't retrieve your way out of it. You can put like 70,000 ICD codes in a context window and ask the model to figure it out. Now here is a clean model to look at it. You use RAG when the knowledge is in your documents. You use fine-tuning when the knowledge needs to be in the model's weight. So RAG gives you a model, a book to read before answering. Fine-tuning changes how the model thinks. Domain-specific language, reasoning patterns, clinical abbreviations, you want to do fine-tuning. And in this video we're going to find that out and we're going to do it efficiently. Now we are not going to fine-tune the entire model, which is, you're talking about billions of parameters. Now we're going to use a technique called LoRA, where you just fine-tune a fraction of the model's parameters and you get most out of it. I'll show you exactly what that means when we get to the training cell. Alright, so it's time to run the notebook. So now what I'm going to demonstrate is a failure scenario. So in this, first of all, we're going to load this open source model, which is Qwen 2.5, 14 billion instruct. We're going to use A100 GPU and we're going to load this in bfloat 16 so that it occupies only 28 GB VRAM. We are going to load the full model. We are not doing any kind of quantization. What we're doing is we are loading the full model and we're going to ask 6 ICD code questions. The first type is it's called code lookup. So in short, you give a code and you ask the model what the description of the code is. The second type is you give a description and the model should predict what the code is. And we expect the model not to answer all the 6 questions correctly. So that's the failure scenario. So quickly running through the different cells. So we first install the dependencies and then we define all the 6 questions. The first type is code lookup, the second type is code prediction, and then we load the quen 2.5 14 billion instruct in b float 16. This is how we do it, and then we run the base model for all the 6 questions. Once this run is complete, we are going to do some analysis on what went wrong. So this is going to take a while, so I'm just going to pause this video and come back once the run is complete. Alright, so we are back, and what you see is the notebook run is now complete. Now what we're going to do is we're going to put all the responses into a whiteboard and do some analysis if the model actually did a good job answering all those questions. Here we go. Alright, so what you see is the first question, it got it right. It was a clean lookup and the answer was correct. Now let's look at question number 2. Question number 2, I think it just made up the definitions. It got it wrong. It was asked to explain the difference between the two codes and it confidently described it, and it got both the descriptions wrong. The next question, it was the right code but wrong disease. So it took a heart failure code and described it as a blood pressure problem, and it did it with a lot of confidence. Question number 4, I think it played it too safe. Now given the clear clues pointing to that specific diagnosis, it should have done a good job. But I think what it did was it went on to a vague catch-all answer instead. Question number 5, I think it just invented a code that does not exist. And question number 6, the final question, it gave a right name but wrong code. So what you see is the model didn't do a good job. The only question it was able to answer correctly was the first one. The rest, mostly it was hallucination. It made up its own code, but it sounded very confident. Now what we're going to do next is we are going to use the LoRA technique to train the same model and see how it performs. Alright, so we completed the baseline run and we saw those 6 examples and it did not perform well. And the reason for that, the model was not trained on that specific domain for the ICD-10 code prediction, and that was kind of expected. As you saw that the model did not predict the codes right, it invented new codes, it had a lot of hallucinations. So now what we're going to do is we're going to fix this using this notebook. We are going to fine tune the base model with ICD-10 code prediction using LoRA. For that, there are like 4 distinct steps we have to follow. The first one is build the dataset. The second is load the base model in a 4-bit QLoRA and attach adapters. The third is train only the LoRA adapters using SFTTrainer. And finally, save the adapter and evaluate on the 6 questions. So the first step is building the ICD-10 training dataset. So we download the official CMS ICD-10-CM datasets from the public domain, and we create 3 distinct examples out of it. The first one is code lookup, which means that you give a code and it will give you a description back. The second one is reverse lookup. In this case, you give a description and it should predict the right code. The third one is differential. In this, you're just comparing 2 distinct codes. One important thing we also do is we split this dataset into 80% training set and 20% evaluation. And the reason for that is we train the model using the training data set and we keep the evaluation data set to see how the model performs, because it has not seen the questions in the evaluation from the evaluation data set. So once that is done, once our evaluation data set is complete, the next model is load the base model. We load the base model into a quantized form and then attach LoRa adapters on top of it. Now let me walk you through that step in a second. So yeah, this is where we reload the model with QLoRA. We quantize it into a 4-bit precision, and then we attach adapters, LoRa adapters, and then we would move on to the next step where we would just train those LoRa adapters. All right, so this is where we're going to run the supervised fine tuning. So in this step, what we do is we take the training example, we send them to the model, and we compare the model's answers to the expected answers. We calculate the loss, and then we update the LoRa adapter. We train it for a few epochs. In this case, we are running 3 epochs as it's configured over here. With each epoch, what we do is we check the evaluation loss on the held out 20%. If the training loss and the evaluation loss both go down, then it just means that our model is doing well, and that's a good sign. Now, if the training loss goes down and the evaluation loss goes up, then the model may be overfitting. It just means that the model is not going to give you accurate responses. Now, we run those 3 epochs, as I said, and once the training is complete, we save the LoRa adapter. Now, we don't save the full baseline 14 billion base model. We just save the adapter what we have trained, and we can reattach that adapter to a base model, whether it's quantized or not. So that's one way it's that's really good. So once the adapter is saved, the training is complete, then we run the same 6 questions, and we will evaluate how the model performs. All right, so now the run is complete, and before we jump into the evaluation results, let me highlight the 4 or 5 important parts from this notebook. So the first part is we're creating the data set, and we are splitting the data sets into 80%, 20% training and evaluation sets. The next is we're loading this model with 4-bit quantization, and what you see is the total VRAM now it uses is 9.3 GB, and this is all the power of quantization. Number 3 is the trainable parameters. So in this case, what we are doing is we are training 8 on 68.8 million parameters out of the 14 billion. This is like less than 0.5%. So we are only training the LoRa adapters while the base model weights are completely frozen. Now let's look at the actual training loss. So what you see is with every epoch run, the training loss goes down, which is good. And we also see the accuracy remains stable. Now, these are all good numbers, which means that the model is not memorizing, but it's learning the new domain. Finally, what we see is the adapter size is saved, which is 273 MB. All right, so now we've looked at the important parts from this notebook run. Now let's look at the answers from this notebook. All right, I'm going to post this in a whiteboard, these answers, and we're just going to quickly look at the 6 questions and how the model performed. So here we go. All right, so question number 1. It was a code lookup and it got the right code and description. Question number 2, again, it was a differential question. And the model correctly distinguished both the codes J18.0 and J18.9. The next was a code lookup and it got the right code. Number 4 was a reverse lookup and it read the clinical note and predicted the right code. Number 5 again was a reverse lookup and it got the exact match. Number 6, it was a reverse lookup and unfortunately it was the right family, but it got the wrong subtype. So overall, great. It got 5 out of 6 right, which is, I believe it's really good, right? Because we had trained this model into a handful of parameters and a handful of examples. So what we have to do now is we have to rerun this workflow, giving more examples. But the important thing to remember is now we're going to just train or retrain the 273 MB adapter and not the full model. Now, this might take you around 50 minutes, but that's a workflow. So until you get it right, you keep running the workflow and keep retraining this adapter. All right, so it's the end of this video. So that's a lot of fine tuning in action. So you saw this in this video that we took a model that failed in all 6 questions. Then we used a lot of fine tuning and we got at least 5 out of those 6 questions right. Now, if you like similar video, please hit like and subscribe so you don't miss any of these videos. And more videos will be coming on small language model and how to make them work in real world. So until then, see you in the next video. Bye for now.